Hello, everyone, and welcome to Amii's November AI Meetup. Let's get started so that we can get you all out of here on time. My name is Sheikh Jubair, and I'm working as a machine learning scientist here at Amii on the advanced tech team. I got to work on lots of really cool projects, and the most frequent questions I got is which one is my favorite project? And my answer is always all of them, because all of them have different challenges and it has lots of different new things we need to do in these projects. In the screen, you can see a QR code now. If you scan this QR code, it will bring you to the sign up page for the Amii newsletter. This is the best way to keep track of what's going on at Amii. You can also follow us on the social media to keep up to date with job posting, research and industry events, and new and exciting programs. Our next meetup is going to be in January. I wanted to take this opportunity to mention that early bird tickets are available for Upper Bound 2023. At Upper Bound, you can expect a deep dive into fundamental research in AI, merged with a parallel exploration of excellence in industry application, 4 days of panels, demos, social, and academic conversations in Edmonton, Canada. This annual conference is poised to be one of the Canada's largest convergences of AI researchers and applied professionals. For more information, talent bursary applications, or to purchase tickets, please visit upperbound.ai. As some of you may be aware, November is Diabetes Awareness Month. We've dedicated our November meetup to a diabetes-related talk in order to help raise awareness for diabetes research. Diabetes is a disease in which your body either can't produce insulin or can't properly use the insulin it produces. No matter which type someone is diagnosed with, living with diabetes isn't easy. While there have been advances in management to better support people living with all these types of diabetes, there is still no cure for the more than 11.7 million people in Canada who are living with diabetes or pre-diabetes. Every day, 640 Canadians are diagnosed with diabetes. That's one person in every 3 minutes. For more information or to find out how you can support those in your life with diabetes, please visit diabetes.ca. And now it's time to get our talk started. I would like to welcome Neil Borle from University of Alberta. Neil will discuss the hurdles he encountered while using machine learning models to predict changes in the blood sugar levels of people with type 1 diabetes. Neil received his MSc in computer science from the University of Alberta under the guidance of Amii fellow Dr. Raj Greiner in the area of applied machine learning. Since then, he has worked at 2 startups using machine learning for wearable devices and computer vision for retail loss prevention, respectively. Currently, he works for ATB Financial as a principal data scientist and developing machine learning solutions for retail banking. And to add, Ras is also here with us. So thanks, Ras, for joining. Over to you, Neil, now.
Great, thank you for the introduction. So I'm just going to select the right screen. And hopefully everybody can see that. So today's talk is going to be on my work related to my master's. So from a little while ago, but the corresponding paper for this work was published actually just last year. So yeah, so in this presentation, going to go through the following. So going to give a brief introduction to type 1 diabetes, the problem that we're working on, applying machine learning to try and forecast blood glucose changes. So a little bit on the background work, the data we were using, some of the modeling, and then the results and conclusions. So first of all, so what is diabetes? So typically with diabetes, well, starting with blood glucose, when you ingest food, and in diabetes diaries, typically we're keeping track of carbohydrates. So when you ingest food, generally though, you end up with blood glucose in your bloodstream. So the problem is with type 1 diabetes, the high blood glucose can lead to damage over time. So we're looking to try and control that. So high blood glucose will trigger insulin to be secreted from the pancreas. And the insulin actually allows the blood glucose to go into the cells. So again, like if the insulin isn't allowing that to happen, then you'll have the high blood glucose. So
I mean, you're still sharing the opening slide. Did you? Yeah, thank you.
Oh, okay, that's interesting.
Thank you.
Maybe I have to be on another screen. All right, so I'll just stick on this screen then. So, so with type 1 diabetes, the insulin-producing cells are destroyed, and it diminishes the ability of the body to regulate the blood glucose because the insulin isn't present and isn't able to, the insulin isn't able to bind to receptors, and blood glucose doesn't enter the cells. So that being the case, then you get hyperglycemia. So this is when the blood glucose is exceeding 8 millimoles per liter. And that long-term can be problematic for patients because you'll get organ damage and various other issues that can arise from consistent hyperglycemia. So there are tests, for example, HbA1c, to kind of see if someone has diabetes by looking at how much glucose is binding to hemoglobin. But yeah, generally the problem here is trying to control the blood glucose. So how do they deal with it? So patients typically self-administer insulin. So this has happened several times a day, but it's directed by a healthcare team according to a regimen. So we want to maintain the blood glucose between 4 and 8 millimoles per liter. And again, trying to avoid hypo and hyperglycemia. So hypoglycemia, the blood glucose is going really low. Hyperglycemia, the blood glucose is really, really high. So the regimen is set by the endocrinologist who's dealing with their patient. And it's usually calculated according to the formula below, where the denominator in these two parts of the equation are parameters set by the endocrinologist after studying the diabetes diary or the data collected by the patients and then given to the endocrinologist. So the target blood glucose here, typically we want it to be like 6 millimoles per liter, right in the middle of the range. So I was talking a little bit about a diabetes diary. So this is what patients are using to keep track of blood glucose fluctuations, and they keep track of that along with other information such as the amount of carbs they're eating, the time of day, the meal. And so this is actually what a diabetes diary looks like. For example, it's just the patient recording the information, often handwritten, into the diary itself. And then this whole book gets passed over to the endocrinologist. So now we'll move on to the actual problem with statements. So what we're trying to do is help endocrinologists manage diabetes. And so this is a control problem, right? We want to know how much insulin the patient should be injecting to kind of get a reasonable blood glucose level. So, and again, we want to keep it between 4 and 8 millimoles per liter. So with a control problem, you can try to directly apply techniques to do control, but another way to look at the problem is to break it down into two subproblems, which is to accurately model the blood glucose dynamics and then apply control on that. So this work is focused primarily on the modeling component. So trying to build a model that, given inputs and some time delta into the future, what the blood glucose would be. So for example, if you have X, a bunch of inputs into the model, and you say, I want to give 1 unit of insulin, then it might say, the model might return or infer that the blood glucose will be 10.3 millimoles per liter. With 2 units, if you give different input to the model, it might say, oh, it's going to be 8.1 millimoles per liter. And with 3 units, it might say, okay, blood glucose is going to be 6.5. So then with that model of the dynamics, you then would choose the input that's of insulin that's giving you the values that you're interested in. So generally, we can look at it like this. So the model, the green box, is taking inputs such as current time, carbohydrates, blood glucose, bolus and basal insulin, among other things, as well as at what point in the time we want to, in the future, we want to make the prediction. So for example, if you know it's 8 a.m. breakfast, and you have eaten 20 grams of carbs, and your current blood glucose is 3.8 millimoles per liter, and you have injected 1 unit of insulin, we're trying to predict, okay, what will the blood glucose be at lunchtime? So this is like several hours later, and that's the purpose of the model in this study. So it might be 3 millimoles, or 13, sorry, millimoles per liter. So then the model, having predicted 13, might in fact actually be 14 is the real value that we observe at lunchtime. And then we can continue making predictions onward from there. So now that we know lunchtime, what do we think supper time is going to be given 10 grams of carbs and 5 units of insulin? So then it might be 8 millimoles per liter is what the model infers. The reality might be 8.8, so we're off by a little bit, and we continue onward from there. But that gives you an idea of what we're predicting, and then also what kind of error signal we get to inform the model as to its performance, particularly in training time. So previous works on blood glucose modeling. So there had been a lot of studies up to this point when I was doing this research with Russ, but they had some limitations. So some were that captured over fairly short periods of time, such as like 3 to 22 days. And other ones had small numbers of patients that they were studying. So for example, there were publications that only dealt with a single patient. Many treated the problem, instead of trying to model the dynamics in general, they just tried to treat it as a classification problem, hypoglycemic or not. And then there were other larger data sets used in other studies, but they were regarding type 2 diabetic patients. So what we did in this study is we worked with a data set that was captured locally at the U of A and was quite large at the time we were publishing. So as far as we know, it was at that time the largest data set available of type 1 diabetic patients. Okay, so now the kind of data we had. So we had 47 patients with type 1 diabetes with a combined total of 29,000 records in their diabetes diaries. So every patient that we included in our analysis had to have at least 100 records, but there were some that went up to 4,000 records. So you can imagine that's several years of consistent monitoring of their diabetes in the diabetes diary. So we had 16 patients with insulin pumps. We had demographic information about those patients as well, including age, height, pregnancy. And then we had, in general, in the data, a mean kind of prediction horizon of 5.1 hours, where the median was 3.7 hours. So that's kind of how far into the future we're trying to predict the changes in blood glucose. So one thing to note that's, I think, important to this study was that what we're dealing with is the data typically collected in the diabetes diary. So we're not, like there are other things that could be collected, but when we were doing this study at the time, it was more about, okay, if the patient walks into an endocrinologist's office, what kind of data does the endocrinologist actually have access to at that point in time in order to design or determine the coefficients for the regimen they would be following. Okay. So yeah, so this was the system where we collected the data, and there are papers published previously on this topic and the collection of the data. Yeah, so this is kind of the interface where we extracted it. Okay, and then some of the patients, they had insulin pumps, so they had pump values settings on their pumps where they're having insulin consistently injected into their body through the pump as well. So that was another feature. So overall, we had the meal time, so before breakfast, after breakfast, etc. Date, time, blood glucose values that the patients had entered, carbohydrates they ingested, bolus insulin, so the rapid acting insulin, basal insulin units, the background insulin, exercise values, so kind of what their level of activity was at the time when they were recording, and the pump value associated with the insulin pump shown previously. Okay, so pre-processing and feature extraction. So in pre-processing the data, we had to, the data of course wasn't 100% clean, so there were some modifications we need to make to it. The first one was removing blood glucose values, removing entry records that didn't have blood glucose values or dates. So we thought those two components were fairly critical to the model to be able to forecast out what the blood glucose values would be. So we simply removed those ones. For blood glucose values, we had some entries that were 0. So the person would have been using the blood glucose monitor to get a reading. And so we knew that the monitors have some inaccuracies with very low values. So it might have been telling them 0, but that wouldn't be the case because if their blood glucose was 0, they wouldn't be alive at that moment. So for that kind of inaccuracy, we opted to set those values to be 1 millimole per liter. And then we took a few different approaches for missing carbohydrate and bolus insulin values. So we kind of generated different copies of the whole data set based on different ways of dealing with those values, and then applied our models to those. So after pre-processing, we had kind of the meal, day of the week, exercise value, etc. We added in some lag values as well. So like most recent carbohydrates ingested, insulin, bolus insulin injected, last blood glucose values, for example. And we also added in insulin on board. So it's an estimate after having injected the insulin, the patient doesn't immediately use up all of the insulin. So there'll be some left over for a period of time. So we also had a calculation for that. So we tried to capture features that would allow us to say, at this point in time, we have everything we think we would need to be able to make a prediction for the next however many hours to infer what the blood glucose would be. So the insulin on board that I was just talking about. So we worked with a collaborator on this project and an endocrinologist in the field. And he helped us to design this curve. And it basically is just a representation of how much insulin would be left over in the body, so residual insulin after some duration. And that went in as another feature into the model. Okay, so we, like mentioned previously, we generated a bunch of different dataset variants, trying to get reasonable performance. So we, for example, we'd throw out carbs or bolus values that were missing, or impute 0 or impute average values. We also tried omitting or including certain features such as day of the week, basal insulin, and then also including or omitting patient-specific features. Trying some tricks, I guess, from the machine learning literature, so like PCA, to do reductions on the features. And then we also tried to replicate a feature set coming from one of the papers we studied by Peter Koch. So he kind of came up with this set of features that he thought were pretty good. So we also tried including those, like massaging our data to fit those features. And then we also had expert feedback from our collaborator as to which records would be like really, really hard to make predictions on. And so maybe we shouldn't try even making predictions on those records. So with Peter Koch's features, this was kind of the listing of them all. The one we couldn't get was stress because we actually didn't have that in our data set. But the rest of them we were able to kind of massage the data to make it fit into that format and test it out that way. So with expert feedback, so we talked to our endocrinologist collaborator, again, like which records would be just too hard to predict. So we kind of came up with this set of criteria. So the first one is the first record, or sorry, the preceding record to what you're trying to infer in the future. Preceding record can't have a hypoglycemic event because the rebound of coming off of a hypoglycemic effect kind of makes it quite difficult to predict what the subsequent value would be. Number 2 was the blood glucose reading must be present for the preceding meal. So if you're trying to, predicting 5 hours in the future or 3 hours in the future is already tough enough. If you're trying to predict like 7 hours, 10 hours, then it's too hard. So get rid of those records. And then finally, the 6 of the last 8 days prior to the prediction must have records for the current meal time and the previous meal time. And so on the next slide here, for example, that means if you're trying to predict, let's say lunchtime, then you have to have lunch and breakfast for the preceding 8 days in order to be confident that you can make that prediction. Oops. And so two more examples of where we wouldn't predict. So we wouldn't try and predict bedtime if we didn't have any records for supper, so a missing entry. And again, with the hypoglycemic event, if that happens at supper, then it would be tough to predict at bedtime what the blood glucose value would be. Okay. So after applying that set of rules to our data set, our data set variants, we generated, again, more data set variants where we include only the subsets that were expert predictable, as we're calling them. But in terms of the number of records we're checking, it's basically the purple and green together is all of the records for each patient. And then the green by itself is the number after applying those exclusion rules. Yeah. All right, so moving on to model evaluation. So when we were looking at this problem, like one simple way to kind of measure how well the model is performing is to just look at the absolute difference and say, for example, blood glucose was 11 millimoles per liter and we predicted 10 millimoles per liter, so we're off by 1, for example. And that here with these, I'll also show you in these two scenarios. So for example, if a patient has a blood glucose that is 3 millimoles per liter and we predict 5, then the error is 2 millimoles per liter. In another scenario, though, we do the same thing. Blood glucose of the patient is 10 millimoles per liter, and we predict 12, and the error is 2. But knowing something about diabetes, we know right away that this is not kind of the best way to measure the success of the model, because the first scenario, where the patient is hypoglycemic, is much more potentially dangerous to the patient than and immediately dangerous to the patient than scenario number 2, where they're hyperglycemic. So instead, we wanted to also include a measure of relative L1 loss. So this is sometimes called in the literature MARD, M-A-R-D. It's kind of a variant of that without the percentage, but we also wanted to include that because if we look at scenarios 1 and 2, when we use the relative L1 loss, and I'll show you in a second what that means. Scenario 1 is emphasized with a loss of 2/3, where scenario 2 is has a loss of 1/5. So now with the relative L1 loss, scenario 1 is has much more penalty to the model. So about 3.35 times more penalty in the first scenario where they're hypoglycemic. So the relative L1 loss is very simple and comparable to absolute loss. So basically, if we just look at the absolute difference between prediction and true value, that is already better than squared error, because if we know that hyperglycemia isn't as bad as hypoglycemia, then squared error is just penalizing the very large numbers already. But then if you take the absolute loss and you divide it by the true blood glucose value, then you get that relative L1 that we were talking about. So I'll show you an image here of what this means. So maybe it's a little bit more intuitive. So basically, if we look at the bottom right-hand side, we see, for example, predicted blood glucose. So we see a marker there for 10. So if, for example, the true blood glucose is low value, 1, 2, 3, but the model predicts a 10, then there's a very substantial error associated with that on the right-hand side. However, on the left-hand side, if the true blood glucose is 15, for example, and we predict like 6, then the error is not nearly as drastic as the other scenario. So that's why we wanted to use this kind of measure of quality for the model. Okay, so now we'll move on to the different models. So first thing is, in this study, we wanted to have kind of a baseline to know how well anything we do is relative to that baseline. So what we decided to go with for that baseline is basically just a naive predictor that always predicts the average value of the sequence preceding the point at which you want to infer the blood glucose. So very, very simple, no machine learning involved in this baseline predictor. And what we thought would be very easily beaten by a machine learning model. Turned out to not be the case, but we'll get to that later. But yeah, just average value of preceding training data. So this is independent of any features or any time duration into the future where you're predicting. The other thing we did to compare what we're doing to kind of a gold standard was compare it to actually our expert collaborator. So we sampled 70 data points from 7 random patients in the study. Then we partitioned that data into contiguous segments, so the data leading up to the 70 points as well. And then we draw the samples one near the end of each segment. And we showed these to our collaborator. He said some of them, like according to those expert prediction rules we talked about previously, some of them are just too difficult. So we ended up with 46 points where we were going to do inference. And we had him make his best guess at what he thought the blood glucose would be, as well as have our model make the same predictions using the same amount of information. So everybody had the same info. We're on the level playing field, the model and the expert. So that was our second kind of measure of quality. So before we get to that, we'll talk about the actual results in a moment, but just to note that we did try many different machine learning models. So these are just some of them. K-nearest neighbor, ridge regression, support vector regression, Gaussian process regression, random forest, and wavelets, wavelet neural networks. But the one that kind of performed the best that we came up with was actually a weighted ensemble of Gaussian process regression. So a little bit of math, so just bear with me here, but essentially what this math is saying, for Gaussian process regression, if you're not familiar with the technique, it basically predicts a whole distribution, a whole posterior, but think of like a normal distribution for every time it is performing inference. So what that means is you get the mean value, what you think the actual value is, as well as the standard deviation around it. So some measure of how confident the model is. So we trained two models, one model and then one set of models, where one GPR was trained over the entirety of the patient's data that was available, right, at training time. Everything that's available at training time, it trains over everything. And then the second model is a collection of models trained, again, what's available at training time, trained over meals individually. So that would be, for example, like a lunchtime predictor, after supper predictor, bedtime predictor. So specific to the mealtime, there would be a model trained on the patient's data. And then that posterior distribution, we'd use the standard deviation to say, hey, this model is a little more confident, this other model is a little bit less confident, and we'd just do a linear combination of those two models, the inference results. So for example, if we're trying to predict at bedtime what the blood glucose is, we would have one bedtime predictor make a prediction, as well as have, so it would be trained on the previous kind of supper to bedtime transitions, as well as another model that was just trained over everything that came before for that patient that it was able to see. And so this was our best performing model. And yeah, so we'll kind of dive into some of the results now. So as mentioned, there were a number of different learning algorithms, a number of different preprocessing steps that resulted in different data set variants. So altogether, 312 of them. So the best one, that weighted Gaussian process regression ensemble, gave an L1 error of 2.72 millimoles per liter. And that was on first data set. The naive predictor gave an error of 2.94. So quite close. So we're not doing super great. We'll talk a little bit more about that afterwards. But yeah, and then we also looked at the L1 error. So the Gaussian process regression ensemble on D9 gave 0.348 for that measure of quality, and the naive predictor was 0.429. So yeah, doing better, but just marginally so. So this is a lot, but it's basically just an image of a heat map of all of the different approaches and the different scores. And the main point of this is just to show you that for the most part, they generally perform similarly. It wasn't like any one model had exceptionally low loss relative to the others. The same is true also using the relative L1 error. Again, things are fairly similar across the board with all these different steps. Some interesting correlations that we noticed when looking at the data is On the left-hand side, we have the loss, and on the x-axis, we have the number of entries. So there was virtually no correlation between how many entries any given patient had and the performance of the model. So this is kind of indicating to us that, again, based on the data from the diabetes diary, what the endocrinologist has access to, really adding more data to the data set is not helping us out here. So another interesting correlation, though, was, which might seem pretty obvious in retrospect, is that the blood glucose variance was highly correlated with the performance of the model. So what that means, just going to the next slide, is that if a patient's blood glucose is pretty wild, going up and down, it's really hard to model it, right? And it's easier to model the ones that aren't swinging so wildly from record to record. And this plot here is kind of showing you, like, yeah, the model that we had for, this is for Gaussian process regression ensemble. It's, you know, not very confident predicting kind of those really large values and those really low values. So all in all, kind of letting us know that maybe there really isn't enough signal here for the model to perform well, given the data that we have. So with comparison to our experts, so we had those 46 data points I mentioned previously, and we compared the M average here, the third column over, is our naive predictor, then the experts' results across the data points, and then our model's results. So fairly comparable on L1. The model does do a little bit better than the expert, but just barely better. And then, yeah, it does perform better than the naive predictor. On the relative L1 error, so this is again emphasizing penalty with respect to hypoglycemic misprediction. So the expert actually performs the best overall, and then both expert and the model do beat the naive predictor, but only slightly. So yeah, so our model is slightly better than the baseline. And that was actually significant in both cases, that the model was better than the baseline, but clinically, and I think that's the important question, is this clinically a big difference? The answer is probably no. And then with respect to the expert performed better on our L1 and our model performed better on the L1. And that kind of makes sense, because if you think about what the endocrinologist is doing day to day, he's not trying to forecast what their blood glucose is going to be. He's trying to set up a regimen, some safeguards, right, to prevent the patient from getting seriously hurt. So it makes sense that he's kind of got a better idea, he or she has a better idea of what's going on with with that kind of low hypoglycemic events and really high events. But whereas our model is specifically just more so caring about absolute difference. And then one thing to note too, though, is just, of course, this is a computational method, and so the computation is quite a bit faster than having the experts sit there and manually try and figure out what the blood glucose is going to be in the next record. Okay, so now the conclusions. Yeah, so we get slight gains, significant but very small gains over the naive model, but they're very, very small and not clinically relevant, really. So, and to illustrate that point, blood glucose value is 6, let's say, for a given patient. If you're looking at an absolute error of 2.7 at inference time, then you might, you might be having the model predicting hyperglycemia or hypoglycemia, because the entire range of 4 to 8 is contained within 6 plus or minus 2.7. So, so again, clinically, that's not very great, because we would want to know what's going on, maybe a bit better than that. So incorporating other patient data unexpectedly did not help. So we did actually in the study, I haven't shown it in this presentation, but we did also try a cross-patient prediction, like using other patients' data to predict our one individual's values, and it really did not do much for the analysis. And so the problem is challenging, the blood glucose modeling, particularly in this setting where you're predicting several hours into the future and with limited data that the endocrinologist can access when the patient comes into their office. And that's kind of shown by the blood glucose error relationship correlation and the lack of relationship between entries and the error. So yeah, and no significant difference between the model and the expert, but both of them did beat the baseline. Yeah, so again, like just to kind of summarize the thought, so we're trying to work with data that the endocrinologist can access when they're seeing the patient in their office, generating that regimen to keep them safe. And so this problem, the way it's formulated is very tough. So it kind of leads us to ask the question, maybe there is something else we can do here, other features to collect or another way of reframing the problem. But just trying to do it this way is going to be really tough. So yeah, we have collected the largest multi-year data set at that point in time for type 1 diabetes. A little bit slow there. We provide a comprehensive study of the data, trying different tricks and techniques to get better performance, but yeah, wasn't able to get clinically relevant results. But yeah, our results do show that maybe there's some opportunity here to investigate other ways of dealing with this problem and trying to address solutions. Yeah, and and finally, we compared our results to human expert, and both are performing similarly on the task, right? So maybe it just requires a rethink on the problem. Okay, and that is it. So thank you for your time. Yeah, any questions?
Oh. So great talk. If people want more information, can you point them to the paper about this?
Yes, I think I had it in here. There we go. I think it just didn't update. Okay. Yeah, so that's the paper. So it was a little bit more recently published, a couple of years ago. I'm not sure, but yeah. So eventually it did get to publication.
Yeah, I have a question. So given the preference of these models on this task, do you still think there is an opportunity for ML to help in this space? Is there any future direction that you can probably guide us?
Yeah, for sure. Yeah. So I think one thing that could help is basically, since this study was conducted and the results were analyzed, tools such as like flash glucose monitoring have become much more prevalent. And so these allow people to basically have a little patch on their arm telling them what their blood glucose is at a much more higher frequency. And so that might be a better way to tackle the problem, because now that they're a lot more available and widely used, trying to forecast shorter time horizons is a much easier problem than trying to forecast like several hours out into the future. So the implications on that might be, the endocrinologist might come up with their general regimen, but then they might also start to think about certain patterns that they see over frequently collected data and how they might deal with those patterns. That is like, over a short period of time, patient blood glucose is changing very rapidly, and how they might respond to that, because now the data is being sampled more frequently, there's more opportunity to deal with that kind of new data.
And, and that's going to also help us with the data collection, right?
Yeah. Yeah, I think one of the key things I kind of realized when working on this was that, yeah, those time horizons, like forecasting so many hours in the future, is just really tough because there's a lot of things, a lot of events, for lack of a better word, will happen in those several hours. So if you change the problem to be forecasting much shorter period of time, you're much more likely to get, I'm sure, results that are a lot more accurate.
We have a couple of questions in the chat. Neil, if you can see that, or I can read it out. So do you want me to read it out, or
if people want to unmute themselves and read their own questions out, that's fine as well.
Yeah, that would be better actually. Valerie, do you want to, I'm not sure whether I pronounced your name correctly, but do you want to unmute yourself and ask the question?
Yeah, I sure can. So I'm coming from a totally different perspective. I'm not a doctor or a researcher. I'm a industrial process control engineer. So it's just kind of fun to see stuff like this and see how weird little esoteric solutions from industry may or may not apply and stuff like this. So first I was curious if this would be something that exists in this realm. Like process plants and processes, whether it's distillation or compression, will often be simulated in software packages made for that sort of thing, of course, taking thermodynamics and all that fun stuff into account. And the question is, when you're dealing with empirical data like you are now, of course, that comes with all kinds of messiness. The same thing in a plant. You do what's called step tests to generate good data. And sometimes it's just garbage. It doesn't always work out. And that's when the folks in operations want to let you perturb their system, which is always a good time. So that's where simulations do come in handy. And I'm wondering, do you guys use that in studies like this so that you can, get those full-on cases where you go, okay, we don't have quite as much messy data to deal with, but I mean, bearing in mind, yeah, it's simulated, it's not real, but it could fill in gaps where, whether it's those patients that have the crazy fluctuating blood glucose, or the patients that just, there's too many holes in their diabetic diary. Has anyone looked at whether simulating this sort of thing might kind of make a few steps in the right direction? That's kind of the first part of the question.
Sure, yeah. I might also get Russ to help out a little bit, but I'll just say that, so there is a type 1 diabetes, or I think diabetes in general, simulation software that had been used in Russ's research group. So there was actually a master's student who came before me who, instead of trying to break the problem down into modeling and then applying control to the model, he just directly tried to apply reinforcement learning as a control algorithm to deal with that. So the short answer is yes, there has been some work done with simulated data, but I'm not super familiar with it, so I'll let Russ fill in any gaps there.
Yeah, so there was a package that we had access to that allowed us to get synthesized patients and try different control regimens. And we did talk to our colleagues and they agreed the model made sense. But we found that we have models that worked really well at predicting and control for the simulated model. We then tried the same policies on the real patients. We didn't change the policy. We saw how well policies worked, and it just didn't work.
That's unfortunate.
The 10 adult patients that they had access to didn't seem to match any of the patients we had, and we couldn't adjust that. But yeah, there are simulators, but they weren't very effective in our case, unfortunately.
Yeah, and that could just be, some simulation packages. It's two things. It could be parameters you may or may not be able to tweak. Maybe it's equations of state. It's getting someone who's on it long enough to become an expert at it and really try to because of course you never simulate something in a simulation package in exactly the same way as it is in real life. Like you come up with idealized trees for a distillation tower, right? I'm sure there's an equivalent for that in the medical field.
The other problem was,
sorry, go ahead.
Sorry, it's just here's 10 simulated individuals. We want to say, here's an individual with this BMI and this blood and this age and so forth. We couldn't fit a real patient into the model.
Yeah.
It didn't reach close to that, which is a frustration.
And so the second part's a bit weird and esoteric too. I'm coming from an older world of control 20 years ago where you did finite impulse response. And so software packages, whether it's Aspen Tech or way back when it was Pavilion Technologies, they were bought out by Rockwell. They're using a different modeling technique altogether. Still making some occasional use of inferentials, like you could use a temperature indicator on a tower to predict a product spec, for example, whether you're meeting impurity specs or not. So there's some similar ideas there. Like machine learning is not new, of course, it's been around for a while, but finite impulse response is a different way to approach it. I have no idea if that even comes up in these sorts of conversations, whether that was just written off as inappropriate for this sort of a study.
So we're here in Edmonton, which is one of the hotbeds for reinforcement learning, which is a way to try to control systems based on the data you observe. And that was my original goal when I first started this, and so we figured we'd solve, to solve the reinforcement learning problem, we'd solve the easy problem of just predicting the future. It can't be, how difficult could that be? And again, another student tried and got mediocre results. And Neil, he tried everything we could think of. I thought something's going to work. And unfortunately, it turned out to be a harder problem than we anticipated. Credit to Neil, right? He persevered and tried everything possible. And the conclusion seems to be it just really isn't possible from the data we have access to.
Well, you're making steps in the right direction. It's really neat to see. I've got diabetics in my family, and it's good to see some progress being made. And by the way, I'm just in Sherwood Park, so we're not that far from each other.
Oh, cool. Well, again, we're fortunate here to have the diabetes, that was at the Alberta Diabetes Institute here, and that's a world-class center which has many amazing results that have come out here. So I was fortunate to work with many collaborators then, and I'm still fortunate to work with many collaborators, some of whom are are attending this meeting right now. But we should go to the next question. Thank you very much for your questions.
Yeah, thanks. Keep it up.
Aniket, do you want to go next?
Yeah. So my question is, like, how much of your inability to predict you think is because of like not having access to the right features? Like, do you think adding some features would help improve the predictions a lot? And what kind of features would you look at?
Yeah, for sure. Yeah. So I think that is probably the key point, is we don't have access to everything that we would like to have access to. And that, again, comes from the study design, where we're intentionally dealing with the data that the endocrinologist has access to. I do think I read in the past a paper, an abstract, where there was a correlation between I think gut flora, I believe, and outcomes on predicting blood glucose fluctuations. But if you think of it from the perspective of, okay, I'm an endocrinologist, I have a patient walk into my office, you may not at that point in time have access to that kind of data. But I think that is kind of what's going on there, is we would need kind of more varied, more data to be able to make better predictions for this problem.
Okay, yeah. So I know that there's like certain people who are like genetically predisposed to have a higher risk, such as South Asians. I think it's a big problem in India. So I was wondering if you like looked at that, like genetic markers or ethnicity, and how much do you think that would affect the prediction? Like, what was the demographic of your data set? Was it mostly like how would you describe it?
Yeah, I don't think we had access to ethnicity information, or at least I don't think I was able to work with that in the data set. The data set was basically patients of a particular endocrinologist who went to his particular office. So it's hard to speculate, how much that information would change the results here. Because, the other thing to keep in mind too is we were typically building models on individual patients and performing inference on those same patients. So in that scenario, the ethnic data or other demographic information is essentially a constant, right, on every vector, if you're just training and predicting on individuals. Perhaps it may have helped, like cross inference or cross patient inference. But yeah, we didn't really have access to that data at the time.
Okay, thanks.
Yep,
Thanks for
no
that.
problem.
And the selection criteria was basically everyone at this endocrinologist's office who had enough records. So that was the only criteria we used, of course.
Yep.
The next question is from a world-class diabetologist. Peter, you want to ask your question?
Thanks, Russ. You're very kind. And I do need to jump off in a couple of moments, but just to say, it is complicated. I think what we've learned from finger sticks is that, it misses lots of oscillations in between. The CGM data is much richer. You've got samples every 5 or 15 minutes. And I think the comments which you've alluded to and others in the questions are that sort of behavioral factors, are going to be key. Somebody might have quite smooth and predictable blood sugar levels, partly because of biology, but also partly because of behavior. They eat predictably, they get their doses right, they get the timing of the doses right. And so I think my hope is that in the future we'll have kind of CGM devices, continuous glucose monitoring devices with accelerometers. And if we could, sort of photograph the plate and calculate the carbohydrate without people needing to guesstimate it, that would give us a lot of richness. But I do think that, again, those dietary and behavioral things may be really key for some individuals, even with the richer glucose data. But again, we're working on that with Russ, and maybe we'll come back and with a suggestion of maybe how we're doing better. But thanks for the inclusion today, and I'm going to have to jump off, I'm afraid.
That being said, so we have only 1 minute remaining now. So I was looking at my clock and that was saying 2 minutes, but now it's just 1 minute. So yeah, so so for respecting everyone's time, we need to sign out. And before signing out, I just want to quickly share my screen. Yeah, so thanks everyone for joining us. We truly appreciate you taking your time to join us today. Just a quick reminder that our next meetup will be in January, not in December. So thanks everyone again for joining here.